Okay, folks, this is the second lecture for tonight's snow day. This is over section 4.9 on finding what are called antiderivatives. So antiderivative refers to finding a function that will give us a specified derivative. It's working backwards with derivatives, and it's actually, it's sort of an interesting topic in its own right, but we're going to find out that it has a fundamental role in calculus going forward. So let's go ahead and give a definition here, a formal definition. Suppose we've got a function f that's defined on an interval I, then a new function, which I'm going to usually use a capital F for. There's kind of a purpose behind that notation. A new function, capital F, is called an antiderivative of lowercase f if the derivative of capital F is lowercase f for all x on that interval. Okay, so for this first example, we're not going to calculate the antiderivative. We're just going to confirm that capital F of x here is an antiderivative of the secant of x. Well, I'm claiming that if I take the derivative of this, I will get the secant of x. How should I check that? Well, let's check by actually taking the derivative. So we get that f prime of x, so the derivative of capital F of x, is the derivative of, let's see, the derivative of the natural log of an expression is 1 over that expression times the derivative of that expression. Let's see here. Well, the derivative of secant x is secant x times the tangent x, and we're going to add to that the derivative of the tangent squared, which is secant squared x, and then, of course, what was the derivative of 20? I'll just add a plus 0 there. So let's see how things clean up. Well, both of these terms have a secant in them that I could factor out. So let's see here. I guess let's first write it as a single fraction. So we have secant x tan x plus secant squared x all over secant x plus tan x, which is equal to the secant of x times, so I'm going to factor this secant and one of these secants out, so secant x plus, I'm sorry, that's a mistake, tangent x plus secant x all over secant x plus tan x. But these two factors here, this factor here and this factor here, those are the same factors, so we can cancel them out. And indeed, like we were hoping to show, we're just left with the secant x. I'm going to pause the video while I fix this. Okay, so we're asked to give two other functions whose derivative is the secant of x. So I'll give one. I think that this function right here, this is an antiderivative. Oops, I messed that up. Sorry, folks. So I think that one antiderivative is capital F of x equals the natural log of the absolute value of the secant of x plus tangent of x plus 30. I think that if I take the derivative of this, I will also get secant x. Do you agree? So you go ahead and give one more function that also has as a derivative the secant of x. So pause the video and do so. So I don't know which one you came up with, but here's one. Here, g of x equals the natural log of the absolute value of the secant of x plus tan x minus the square root of 2. This would also have as its derivative the secant of x. Okay, so maybe you see what's going on here. And in fact, if you remember way back at the end of chapter 3, we had a proposition that said two functions, if they share the same derivative, then they can differ by at most a constant. Okay? And here we say that in another way, we say that two antiderivatives differ by at most a constant. Okay, I'm not going to reprove this, but if you go back to, I believe this was in our section, Actually, it wasn't in chapter 3, it was in chapter 4. This was in section 4.2, I believe. Section 4.2, I think. You can go back and look at that theorem and how we proved it. Okay, so we just said that all three of these functions, the one I gave you to begin with, this function here and this function here, they all have the same derivative, secant of x. So we could then go ahead and say that the antiderivative, so here I'm using the definite article the, would just be one antiderivative plus an arbitrary constant c. Okay? Sometimes books will call that the most general antiderivative of f. Basically what it means is if I want to encapsulate all possible antiderivatives of a function, I just give one of the antiderivatives and add an arbitrary constant c. So c just stands for an unspecified constant, or you could think of it as giving you a family of functions. Okay, so here I'm asking you to give the antiderivatives of the function 3. So for the function f of x equals 3, what are its antiderivatives? Well, the antiderivative of this function is what? Well, I'll let you think about it for a minute. What function, when I take its derivative, gives me 3? Pause the video and go ahead and give it an answer. So the answer is that any function of the form 3x plus a constant will give me as a derivative 3. So we're going to write that as 3x plus, and then that c is that incorporates the whole family of functions, all of whom have this as its derivative. Okay. All right, so go ahead and pause the video, try to work the rest of these. Some of them might come quickly to you, some of them might take a minute, but go ahead and give the antiderivatives of these remaining functions. Pause the video and do so. Okay, so an antiderivative for g of x equals x squared, an antiderivative of this would be capital G of x equals 1/2 x squared plus c. Okay? If you don't believe me, the easiest way to check to see that you indeed have the antiderivative is just take the derivative of this, just like I did in my very first example. What is the derivative of capital G of x? Well, this 1/2 comes along for the ride. You bring down the power of 2. The 2 and the 1/2 cancel. Folks, I just stepped in it. I'm sorry. I'm kind of on autopilot right now. My apologies. What is an antiderivative of this? It would be, well, pause this. Okay, hopefully I'm done with this pen fiasco. So what is an antiderivative of g of x equals x squared? Well, it's 1/3 x cubed plus c. So folks, I was completely wrong just a moment ago. How do you check to make sure that the derivative, that capital G of x is an antiderivative of lowercase g of x? Well, I take the derivative of capital G of x, and sure enough, I bring down the power of 3 times the 1/3. Those cancel, subtract 1 from the exponent, so I end up with x squared, and then the derivative of any constant term is just 0. So yes, indeed, this is the general antiderivative of x squared. Okay. So which function has what is the antiderivative of sine of x? Well, if I say that, I don't know, maybe k of x is equal to sine of x, which function gives sine of x as its derivative? Be a little careful here. Okay. It would be minus the cosine of x plus c. The derivative of minus cosine of x is in fact sine of x. So be careful with that. Now that we're going in both directions, the derivatives of your trig functions are going to be especially problematic with those negatives. Okay. Here's a nice one. If I give you the function f of x equals e to the x, what's its antiderivative? Well, it's capital F of x equals e to the x plus c. Okay. What if I gave you the function g of x is equal to 1 over x? What function has 1 over x as its antiderivative? Well, I'm going to give, let's go ahead and I should maybe have added to this. Here we're going to assume that x is positive, because then I could say that its antiderivative is the natural log of x plus c. Notice now if I take the derivative of this function, I do indeed get 1 over x. So folks, we're working backwards here. We're working backwards here. let's try a little bit harder one. Let's find all functions g so that g prime of x is equal to this expression here, this long expression. Okay. Well, until you get good at differentiation, this is sort of like when we first had to practice, until you first get good at antidifferentiation, you don't have a lot of potential rules. I'd like to rewrite this function before I keep going. I'd like to rewrite it as 4 sine of x plus 2x to the fourth minus x to the minus 1/2. So what did I do here? I divided this x into both terms. Okay. If I lost you on that very last one, remember, so I could rewrite this. I could write this part of the second. I could write the second term as 2x to the fifth over x minus the square root of x over x, which is where I got the 2x to the fourth. Here I would have minus x to the 1/2 all over x. When I subtract 1 from 1/2, that's where I got this negative 1/2 from. Okay. So what functions have this as its derivative? Well, this is going to be a little bit harder working backwards. I claim that the answer is minus 4 cosine of x plus 2/5 x to the fifth minus 2x to the to the positive 1/2. 2x to the positive 1/2. Now, I think this was a challenging problem to come up with. We were given g prime of x. I rewrote it in this form. Now we're trying to find its antiderivative. I think that I might have lost some of you on this. That's okay. We're going to develop some general rules for going forward. But what I do think everyone should be able to follow is, let's check. Does g of x have this as its derivative? Well, we could check, right? The derivative of minus 4 cosine x would be 4 sine x, so that term checks out. What's the derivative of 2/5 x to the fifth? Well, it's 2x to the fourth, so that checks out. And then let's check this one. Using my power rule, I'd bring down the 1/2, which would just give me a minus 1 for the coefficient. Subtract 1 from the exponent, x to the 1/2. Okay, so this is an antiderivative, okay, but it's not the general antiderivative until I put plus c there. Okay, so let's just clean up the answer just ever so slightly. We'd have minus 4 cosine x plus 2/5 x to the fifth minus 2 square root of x plus c. And it turns out that if I take the derivative now of g, I would get back to this function here, which is the same as the one we were asked to work with. Okay, so let's keep going. Okay, let me pause the video. Okay, folks, I had to pause the video. I'm realizing I think I'm missing a rule in these notes that I think I'd like to go ahead and give you before we go forward. Some of these antiderivatives just come down to the fact that you've memorized your derivative rule and you just apply the rule backwards. But we are going to develop some rules for antidifferentiation, and I'm sort of feeling like to continue forward, I'd like to give you one of those rules now. So this is off to the side, and my apologies that it's not a built-in part of the notes. Okay, so I'd like to give you the power rule for antidifferentiation. Okay. So recall that if I have f of x equals x to the n, that the power rule for derivatives says that gives me n x to the n minus 1. Okay. Well, I'd like to give a antiderivative rule. So if I give you, so here it is, the antiderivative power rule for f of x equal x to the n. If I want to take the antiderivative of that, I'm going to do this rule sort of in reverse. So I'm going to say it has an antiderivative of, I'm going to, instead of subtracting 1 from the exponent, I'm going to add 1 to the exponent. And then where before I would have brought an exponent down, multiplied by the original exponent, I'm now going to divide by the new exponent. And don't forget your plus c on these. Okay, so let's just check that. Okay, so if I tell you I'm thinking of a function f of x is equal to x to the 6th power, what is its antiderivative? Well, it will be 1 seventh x to the seventh plus c. How did I get there? I added 1 to the exponent, and then I divided by that new exponent. So that's a way to check that that should give you sort of an intuition, anyway, that power rule for antidifferentiation works. Okay? The reason why I want that is I want to keep going with these problems, but we're going to need that rule. I feel like it's the best way to make these arguments. Alrighty, so we're asked to find a particular antiderivative that satisfies two things. First of all, we want the function to have as its derivative x radical x, but we also want to stipulate that it has to pass through this point right here. Okay? So what are we doing in these problems? Well, just a moment ago we said we can find a whole family of functions that have as their derivatives a given derivative. And that's why we always had to put that plus c there. But now we're going to specify which one of those functions that we want. Okay? So I'll talk more about this in class because it's an interesting topic. But let's just go ahead and sort of naively push through this. So we first want to find f, given that we know that its derivative needs to be x times the square root of x. So we know f prime of x is equal to x square root of x. Okay, I'm going to rewrite that as x times x to the 1/2. So I can rewrite this as x to the, let's see, that's 2/2 plus 1/2. So I could rewrite that as x to the 3/2. Okay. So then we know that the family, the antiderivatives, the general antiderivative of f prime is the function f of x. Notice here, since this was a f prime, I'm going to write this as an f. If this were just the letter f, then I'd write a capital F here. That naming convention isn't really a big deal. But to figure out what function has as its derivative x to the 3/2, I'm going to use this power rule for antidifferentiation. So what do? I add 1 to the exponent. So 3/2 plus 2/2, adding 1. So 3/2 plus 1 is 3/2 plus 2/2, which is 5/2. Divide by the new exponent, so I get 2/5, plus your arbitrary constant, c. Okay. At this point, pause the video and just make sure I didn't go too fast for you. But also double check, take the derivative of f and see that yes indeed you get back down to x to the 3/2 by using your power rule in the differentiation direction. Okay, so you bring down the 5/2, that cancels with the 2/5, subtract 1 from the exponent, 5/2 minus 1 brings you back to x to the 3/2. So I think everything's checking out. Okay, so we've got the general antiderivative. It stands for a family of functions, all of whom have x radical x as their derivative. But for this entire family of functions, I want specifically the one whose constant enables me to pass through the ordered pair 1, 2. Okay? So I know that when I plug in a 1 into this function, and I would get 2/5 times 1 to the 5/2 plus c, which would give me 2/5 plus c, I know that when I plug in a 1, I want to get out a 2. So I'm going to set 2/5 plus c equal to 2, and that's going to enable me to solve for that constant. So I get c is equal to 2 minus 2/5, or c is, let's see, 2 as a fraction is 10/5 minus 2/5, so I get that c is equal to 8/5. Now careful, that's not my answer, right? This was just the constant that I wanted to then say that the function that I'm after is f of x equals 2/5 x to the 5/2, plus we determined that the arbitrary constant had to be 8/5 to guarantee that we pass through this ordered pair 1, 2 here. So that's our answer to part A. Okay. So for part B, we again want to have a function f that has as its derivative x radical x. So that part's not going to change. But in this case, we want it to pass through the ordered pair 1, 4. So we want 4 to equal 2/5 times 1 to the 5/2 plus c, or 4 to equal 2/5 plus c. So we find that c is equal to, well, 4 is 20 fifths minus 2/5, so we get that c is equal to 18/5. So what's our answer? Our answer is the function f of x is equal to 2/5 x to the 5/2 plus 18/5. That'll be too big. Let's try this. So that's our answer to the second part. Okay. So let's have you guys pause the video, and I'd like you to try number 9 on your own. There's no difference between number 9 and number 8, other than finding the antiderivative is a little maybe trickier, but it's different than before. So pause the video and give that a shot. So before I that's the wrong size. Before I take the antiderivative of this, let's just go ahead and take one step to just slightly rewrite this function. And for many of you, I think you'll find it helpful if you rewrite the function prior to taking the antiderivative. It'll be a little bit easier to think through. So I'm going to rewrite this as -3/2 x. Okay. So now I'm ready to find the antiderivative to this. So it'll be the function f of x. And it turns out, okay, and you may have guessed this, that we can take antiderivatives termwise. Okay, so if I have a sequence of terms being added or subtracted together, I just take the antiderivative of each one of those, and we'll talk about that in Chapter 5. So what is the antiderivative of e to the x? Well, it'd be e to the x plus c. We'll worry about that c at the end. What function, this one's a little bit more interesting, what function when I took its derivative gave me secant x tan x? So again, we're going backwards here. What function, when I took its derivative, gave me secant x tan x? Well, the answer is secant x. Okay. Then here, what am I going to have to do? Well, I'm going to use my antiderivative power rule. So I'm going to add 1 to the exponent and then divide by the new exponent. So we'd have -3/2. I'm dividing by the new exponent of 2, so I get the constant -3/2 followed along times 1/2 x squared. Don't forget now our arbitrary plus c. Okay, let me clean that up. To be honest, folks, usually when I'm taking the antiderivative of this term, I go ahead and just divide this fraction by 2 all in one step. So I would get -3/4 x squared plus c. So this right here, I didn't mean to underline that as my answer, because we're not quite done yet. But this term right here is the general antiderivative of this function f prime. So if I take the derivative of this, notice that I indeed get this line right here. You should pause the video and check that. Okay. But we're not done with the problem, because we don't want an entire family of functions that has this as its derivative. We want the specific one from this family that also passes through the ordered pair 0, 8. So I know that 8 has to equal e to the 0 plus the secant of 0 minus 3/4 times 0 squared plus that arbitrary constant. E to the 0 is 1. Secant of 0 is, do you remember? It's also 1. Minus 3/4 times 0 plus c, so I get that 8 needs to equal 2 plus c, or c has to equal 6. So at long last, we find that the function we were after is this function right here. F of x equals e to the x plus the secant of x minus 3/4 x squared plus what? Well, not just plus the arbitrary constant, but specifically we need the constant to be 6 in order for us to pass through this point right here. Okay. We'll go ahead and do number 10 here, and then we'll break the video in half. So this is just more of the same in some ways, folks, except that now instead of finding, I'm asking you to find f so that the second derivative satisfies these conditions. So first of all, we're going to take the antiderivative of f double prime. When I take the antiderivative of f double prime, I will have the function f prime. So I'm going to have to repeat this process twice to work back up from the second derivative to the original function. Okay, so let's give that a shot here. We know then that f prime of x, I'm going to apply the power rule here, so add 1 to the exponent, x cubed, divide by the new exponent, so 12 divided by 3 is 4, plus add 1 to the exponent, that'll be x squared, divide by the new exponent, so 6 divided by 2 is 3, minus 4x. Yeah, that's a little interesting, but the antiderivative of a constant is the constant times x. If you wanted to think of it as a power rule, sure, there's a 1 here where there used to be a 0, then you divide by the new exponent. Okay? Plus c. Okay? Now in this case, I'm going to actually have a couple of constants, so I just know from experience I'd like to start numbering these, so let's just call that c1, okay, because I'll have a second constant here in a minute. Okay? So now I'm ready to find f of x, the original function. So we start out with the second derivative. We took the antiderivative to get to f prime. Now we're going to take the antiderivative again to get to f. Okay. So here I'm going to again apply the power rule. I'll add 1 to the exponent. I get x to the fourth. Divide this term by the new exponent. 4 divided by 4 gives me 1. Plus x cubed minus 2x squared plus, and then I'm interested in this part right here. So this is a constant. I don't know what it is, but it is a constant. So what is the antiderivative of a constant? It's a constant times the variable x. Plus, we need a whole new family of functions here, all of whom that have this as their antiderivative. So let's add another constant there. And I should have written that as c. It doesn't really matter, but this was the first constant, so this would be the second constant. Okay. So pause the video, rework through that, see if you have any questions. All of it boils down to using this power rule for antidifferentiation. Okay, so now we need to figure out what these two constants are, because this represents a family of functions, but we need to actually specify what these constants are to figure out which of these family passes through these 2 points. Okay. Well, let's use the first bit of information. We know that f of 0 has to equal 4. Okay. So we know that 4 is equal to 1 times 0 squared plus 0 cubed minus 2 times 0 squared plus c1 times 0 plus c2. And with a polynomial, when you evaluate a polynomial at 0, all variable terms vanish, and so we're just left with the fact that 4 has to equal c2. Okay. So now we know that f of x has to equal x to the fourth plus x cubed minus 2x squared plus c1x plus 4, because we just determined c2 is 4. Okay, well, how are we going to determine c1? Well, the first order pair helped me determine one of the constants. Okay, and so now let's use the second order pair to determine the second one. By the way, folks, this problem's a little bit misleading in that I was able to find one of the constants by using just one of the ordered pairs. In reality, I would plug both these points into the function. I would get 2 separate equations that might both involve c1 and c2, and then I might have to solve that system of equations simultaneously. So these problems can get a little bit harder in determining what your constants are, and you might see an example of that in your homework. But for this one, we're just getting started, so let's see here. We know that when x is 1, it has to output a 1, so 1 needs to equal 1 to the fourth plus 1 to the third minus 2 times 1 squared plus c1 times 1 plus 4. And now let's go determine what c1 has to be to make that true. So we get 1 is equal to, let's see, that's 1 plus 1 minus 2. So those all cancel. 1 times c1 is c1 plus 4. So we get c1 is equal to minus 3. So at long last, we're done with this problem. We know that the function that has this as its second derivative that passes through these 2 ordered pairs is the function x to the fourth plus x cubed minus 2x squared minus 3x plus 4. Okay? And you can confirm, and I would encourage you to pause the video, confirm that when I plug in a 1, it outputs a 1. Confirm that when I plug in a 0, it outputs a 0. And then take the find the second derivative of this function and find that the second derivative is indeed 12x squared plus 6x minus 4.